All right, so this is day 2 for our notes, kind of a summary of the gas law problems with some new stuff thrown in. So the next law we're going to do is Gay-Lussac's law. If the amount of gas and the volume of the container are held constant, the pressure of an ideal gas will be directly proportional to the temperature of the gas. So as the temperature of the gas increases, the particles with more kinetic energy collide with the container walls more often, which will increasing the pressure. So anything we do to make these particles strike the walls more often or harder will increase the pressure. So pressure is directly proportional to temperature. And we have our equation. Of course, P always stands for pressure. K would be a constant. And T would be temperature in Kelvin. It says the following equation can be used to calculate the pressure or temperature of a new state. Remember, this is going to be something where we've got a change taking place. As long as the volume and the number of particles, let's write the word number, which is also known as moles, remains constant. So whenever we've got one of these equations where we've got two fractions, in order to solve this, the first thing we're going to do is cross multiply. We're going to turn this into P2 times T1 is equal to, and then cross multiply the other side, P1 times T2. Now I would just substitute I'd isolate my variable. Let's say that T1 is my unknown. In order to get it isolated, I'm going to divide P2 by itself. If I do it to that side, I'm going to do it to this side, P2. So basically what I'm doing is I'm taking whatever is next to my unknown and I'm sliding it underneath and dividing the other side by it. So let's take a look at a question. A scientist measures the pressure of a particular gas in a closed fixed volume container, and the pressure is 1.25 atmosphere at a temperature of 20 degrees Celsius. The scientist then heats the container to a temperature of 75 degrees Celsius. What is the new pressure in the system? So with these gas law problems, I can't stress enough how important it is to do your knowns and your unknowns. So looking at our question, our starting pressure is 1.25 atmospheres. Our starting temperature is 20.0 degrees Celsius. I'm going to have to add 273. And when I do, I'm going to get 293 Kelvin. I'm going to go for my ending conditions. I'm solving for pressure. My starting temperature is 75.0 degrees Celsius. I have to add 273, and that's going to give me a final a final temperature of 348 Kelvin. So now I'm going to rearrange my formula and then substitute in my values. So when I cross multiply, let me change color here. I'm going to cross multiply this side first. So P1 times T2 is equal to, now I'm going to cross multiply the other side, P2 times T1. Now P2 is my unknown, so I need to keep that by itself. I'm going to slide this over and divide this side by T1. Now I'll substitute my numbers. P1 was 1.25 atmospheres. I'm going to multiply that by T2, which was 348 Kelvin, divided by T1, which was 293 Kelvin. So I put that in the calculator and I solve it. I'm going to get 1.48, and the unit that I'm going to need is atmospheres. And that's how I'd solve that problem. Remember, if a problem provides you with temperature in Celsius, you must convert to Kelvin. Let's go on to the next law. The next one is the Charles law. So if the amount of gas and the pressure of a container is allowed to stay constant, the volume of the gas and the temperature are in direct proportion. As the temperature increases in a container that can expand to provide constant pressure, the volume of the container will increase. Here we have our balloon at a low temperature and our balloon at a higher temperature. Those molecules are going to be traveling faster because of the higher temperature. They're going to hit the walls of the balloon with more force. They're going to hit more often. It's going to increase the pressure, and our balloon will get bigger. So volume and temperature is directly proportional. Another way to write the equation, we would use V for volume. K would be a constant, and T would be temperature. Again, always in Kelvin. The following equation can be used to calculate the volume or temperature of a new state. So again, we've got a change going on here. As long as the pressure and the number of particles otherwise known as moles, is constant. So just like we did with the other gas law problem, in order to solve this, I'm going to have to cross multiply and then isolate my variable. So let's read a problem and pull out our variables. A scientist has a balloon at 22 degrees Celsius with a volume of 1.20 liters. Well, that's my starting condition. The scientist then heats up the balloon to a temperature of 40 degrees Celsius. What will be the new volume of the balloon? So let's pull out our knowns and our unknowns. So volume 1 is 1.20 liters. Temperature 1 is 22.0 degrees Celsius plus 273. And that's going to give us a final temperature of 295 Kelvin. My volume is going to be my unknown, and my ending temperature is 40.0 plus 273 equals 30. Whoops, hang on. That's going to give you a temperature of 313 K. Stumbling over my own words. So now I'm going to rearrange my formula. I'm going to cross multiply this side. V1 times T2 is equal to, cross multiply my other side, V2 times T1. V2 is what I have to isolate. That's what I want to stay here. I'm going to slide T1 over. Now I'm going to substitute in my numbers. V1 was 1.20 liters. T2 was 313 Kelvin. T1 was 295 Kelvin. So I put that in the calculator, and my answer will be 1.27 liters. That's going to be my final volume. Again, if a problem provides you with temperature in Celsius, you must convert to Kelvin. Next page. Now we're going to be talking about the combined gas law. This is actually a really important law to understand how to use. Now your worksheet has all the words with just some fill-ins. Mine, I grabbed the wrong one. So I'm going to tell you what to fill in the blank. The sheet reads, if a scientist considers Charles' law, Boyle's law, Gay-Lussac's law together, they can write an equation called the combined gas law to represent the relationship among the pressure volume, and temperature of a gas. So we're taking all of these and combining them together. So this would be pressure, this would be volume, this would be a constant, and this would be temperature. Again, on your paper it says the K constant in each of these equations will not be the same value. To use the combined gas law to predict a temperature or volume or pressure change, the number of particles must remain the same, because that's our constant. Okay, it must not change. So let's take a look at our formula here. It says the following equation can be used to calculate the pressure, temperature, or volume of a new state, as long as the number of particles does not change. So this is a fraction again, where we've got one fraction equal to another fraction. To solve this, we're going to do the same way we've been doing all along. We're going to cross multiply. So this is going to give me P1 times V1 times T2. Now I'm ready to cross multiply the other side. P2 times V2 times T1. So let's say that V1 is my unknown. To isolate that variable, I need to get rid of P1 and T2, so I'm going to divide them by themselves. So there goes P1. If I do it to one side, I'm going to do it to the other side, so P1. Now I have to get rid of T2, so I'm going to divide it by itself, which means I bring that over here. Now I've gotten rid of that, and now I've got my unknown by itself. And then I just substitute the numbers into the formula. So let's try a problem here. And our problem says a sample of neon gas occupies a volume of 875 milliliters at 31.0 degrees Celsius and 805 millimeters of mercury. So those are my starting conditions. So I'm going to write down all my knowns. So my starting P1 is going to be equal to 805 millimeters of mercury. My volume 1 is going to be equal to 875 milliliters. All right, so my T1 is equal to 31.0 plus 273, and that's going to give me T1 of 304 Kelvin. Now let's do our ending values. P2 is my unknown. My V2 is 925 milliliters. And my T2 is going to be the ending temperature of 50.0 plus 273, which will be a final total of 323 Kelvin. All right, now I'm ready to cross multiply and plug my numbers in. So when I do this, I'm going to have P1, I'm doing this side, V1 times T2 equals, now I'm going to do the other side, T1 times P2 times V2. P2 is my unknown, so that has to stay by itself. I'm going to slide these other two underneath here, so I've got T1. Now I'm going to slide this one under, V2, and I'm ready to substitute in my numbers and solve, because I've gotten rid of these guys. So P1 is 805 millimeters of mercury times V1, 875 milliliters, times T2, which was 323 Kelvin. Now I'm ready for the bottom. T1 was 304 Kelvin times V2, which was 925 milliliters. So I'm going to put that in the calculator and solve for it. When I solve, I'm going to get 809 millimeters of mercury. And there we go. Last page. Now, the last thing we're going to talk about is kinetic energy. So kinetic energy abbreviated KE, of one particle will be equal to 1/2 times the mass. The little m stands for mass. This is a lowercase v. A capital V stands for volume. A lowercase v stands for velocity, which means speed. So this is the formula for the kinetic energy of a particle. This is what you're going to need to recognize for the test. So be sure you can recognize this formula as being the formula for kinetic energy. How this works is kinetic energy of a particle is related to the speed it's traveling and the mass or the weight of the particle. If two particles are traveling at the same speed, but one is larger than the other one, the larger particle has more kinetic energy. If two particles have the same mass, but are traveling at different speeds, the particle moving faster has more kinetic energy. Temperature is directly proportional to the average kinetic energy. Of the gas molecules in a given sample. We'll be looking at this formula in just a second. If temperature increases, the average kinetic energy of a sample increases. The higher the temperature, the faster the particles are moving. This formula here, I'm going to have you actually cross out. You're not going to be responsible for knowing how to use that formula or for memorizing that formula. This is the one that you're going to need for your test. You need to be able to recognize that formula. One last thing to talk about, and that's actually a repeat from what you had in biology. Diffusion is the process by which gas particles disperse or spread out in space. Gas particles do not sense concentration differences. They just move randomly, and by random movement end up equalizing the concentration in the container. So they go from being from high concentration to spreading out to places where there's a low concentration until finally they're all equal in all parts of the container. And that's the end of the notes. Doo-doo-doo.